This is Coppr, an AI hardware engineer that turns engineering intent into a manufacturable circuit board. For this demo, I'll use a deliberately simple voltage divider here, so every decision Coppr makes is easy to inspect. I start by describing the intent. Notice that I'm specifying function and constraints, not drawing a schematic or naming parts. I am prompting for a 20 by 10 mm board with a 2-resistor divider, input through a 2-pin connector, and accessible output and ground test pads. I also ask Coppr to prefer parts from Coppr Cloud. When I hand this to Coppr, the agent reads the existing project and turns the request into typed requirements: the board outline, electrical nets, component roles, test access, and acceptance checks. Think of the backend as a code model of the hardware. On the left is the project structure. It shows the design, parts, schematic, layout, checks, and outputs in one place. The live trace on the right side shows what the agent works in real time. The agent always opens the working view so that the user can stay on track. As we could see on the agent sidecar, Coppr finds one decision it cannot safely infer: the division ratio. That choice defines what the circuit actually does, so the agent asks one blocking question instead of guessing. We chose equal resistors. Coppr calculates a 1/2 ratio, or 2.5 volts from a nominal 5-volt input, and records that decision in the project trace. As Coppr works on parts discovery, it searches for a 100 kΩ 1% resistor, a compact 2-pin input header, and 1.5 mm probe pads. The chosen records correspond to real Vishay and Sullins parts, with explicit manufacturer part numbers. Before selection, Coppr checks resistance, tolerance, position count, package evidence, pin data, and whether symbol and footprint assets can be produced. Each candidate remains inspectable before it enters the design. Here Coppr checks the electrical operating point. With two 100 kΩ resistors and 5 volts in, the nominal output is 2.5 volts. Divider current is 25 microamps, and each resistor dissipates 62.5 microwatts. Coppr also records the high impedance load assumption. The calculation is exposed because an engineer still needs to review assumptions such as loading, tolerance, and derating. With the electrical assumptions checked, Coppr moves to schematic design. It first creates the circuit structure from the typed model or code representation, which is the Coppr design language, or CDL. The input connector, the 2-resistor divider, the output test pad, and ground, and their nets are all first designed and expressed in code, and what the user sees in the schematic sheet is the editable projection of this CDL code. Now the first compiled preliminary schematic is visible. An engineer can inspect the connections, pin mapping, labels, and selected parts from BOM before Coppr moves to board layout. This is fully editable by the engineers. The agent continues to edit this structured model through typed operations. It is not clicking pixels. This first compiled schematic is an intermediate engineering artifact, not a finished board yet. But it already comes from the same source model that drives the bill of materials, KiCad export, layout, checks, and fabrication files. From here, Coppr keeps resolving issues and rerunning deterministic checks, while the engineer can inspect the design and the full decision trace. Now we move from circuit logic to the physical board. Coppr starts with the exact board outline, 20 by 10 mm and 2 layers. It places the connector at the edge. It keeps the test pads open for a probe. It places the resistors between them. The system uses pad numbers and component geometry. so it knows which physical copper pads belong to which electrical pins. This small board makes the method easy to see. At first, the thin connection lines show what still needs to be routed. Each line is a real electrical connection the board must complete. Before routing, Coppr checks the pads, Coppr rules, and board edge. It then turns these required connections into Coppr traces. If a path breaks a rule, it stays visible as an issue. Now with the routing completed, Coppr has started working on the silkscreen labeling. The CDL code backend has the syntaxes precise enough to represent the exact position, layer, size, and rotation of each item, even a small silkscreen mark. That matters because the agent is not just describing the board. It is making specific, reviewable changes to the actual board data. Coppr then checks that these labels remain readable and do not conflict with pads, traces, or the board edge. Now, we're looking into the final CDL script that represents every single thing in this project, including the BOM, every single net, every component rotation, and every silkscreen label, etc. This is what the agent builds and edits. The final view shows the design graph for a selected net. You can see V-in, V-out, ground, the parts attached to each net, and the connections between them. The UI gives the engineer a way to review every change. Coppr makes hardware design faster to create, easier to inspect, and ready to export once the required checks pass.